We're going to be looking at rate of change and figuring them out through graphs. So to begin off with, let's just have a think about how the rate of change can actually change. So let's imagine ourselves a cylindrical cup and that we're filling it up with water. All right, it's a perfect cylinder. Now think about how long will it take for the first centimetre or the first little bit to fill up. Well, it's going to be the same amount of time as it takes to fill out the second centimetre of the cup. Why? Because it is a cylindrical shape, and if the water is running in a constant rate, it's going to fill up at a constant rate. We could imagine the graph of a picture like that to just be a straight line like so, okay? Where we've got time down on the side and distance. As time increases, so does the distance, the height, filled up. Alrighty? So let's now have a think about how each of these more unusual shapes would fill up by the same rules. Well, imagine the cone to begin with. Well, the cone starts off with not very much at the beginning, right? There's not that much water that can fit in this little bit of the cone. It's just a little nib. Whereas you can see on the second centimetre that it's actually going to have a little bit more water. So it's going to take a little bit longer to fill up, and the next centimetre again, it's going to take a little bit more. But notice that there's no sharp bends in the cup, so it's going to slowly but surely take longer and longer to fill up. So the rate at which it fills up will actually slow down in terms of the depth of water. So if we look at this first graph here, at the beginning it has a really steep ascent, but then over time it slowly but surely flattens out and gets a smaller gradient. So that means number one has got to go with A. Let's have a look at number two. Well, number two looks very similar. It's got almost like a cylindrical bottom and then a conical top. So that means at the beginning it should act like the cylinder did, which would mean a straight line, but then after here it should look like a smooth curve. And you can see at the transition point that it's not a harsh transition, it's actually quite a smooth transition. So we're looking for one that has a constant beginning and then it slows down. Well, it could either be B or C. D has a slow start and a fast finish, as you can see here. Fast, slow. So it must be graph C or graph B. The only difference between these two is this one has a bump and this one does not have a bump. And as I said before, that's a smooth transition, so it's going to be the smooth transition here, meaning that graph 2 goes with cylinder 2 goes with graph C. Number 3, we can have a look at, well, it's got a cylindrical bottom, so it's going to be going up as a straight line, and then a cylindrical top, except a much bigger cylindrical top. So it's going to take ages to fill up this centimetre of water compared to this centimetre of water. Alrighty, so we're looking at something that looks like B. Really quick beginning, slows off. By process of elimination, the last one must be 4. We can see why. Big cylinder at the bottom, little cylinder at the top, means that it takes ages to fill up this bit, and it doesn't take very long to fill up this bit. Slow beginning, and then a quick, steep rise. Alrighty, so let's have a look now at how can we actually work out what's called the instantaneous rate of change, meaning on a curved shape, how do we actually know how sloped a point is? Well, that's called the instantaneous rate. We call it the rate of change at that instant, instantaneous. So the question is, well, what's the slope at this point? Well, we could approximate it by just drawing a line like this, but if you actually have a look at, that doesn't actually match up necessarily with the curve below. So we can do something better, and we do that by drawing something which is called a tangent. So a tangent is a line which perfectly matches the gradient at the point that we're interested in. And we can see, if I draw this line right here, that it matches how sloped it is at that exact point. And this line here is what is called a tangent, and it's a tangent to that point 360. Now, although we can't work out the rate of change at that point, we can work out the slope of the tangent, and that is how we're going to work out the instantaneous rate. So the instantaneous rate of change is going to be the change in the temperature over the change in time based on that line. So I'm going to use the points 0, 100 and 70. So the change in temperature is it went down by 100, and the change in time is that 7 minutes passed. So we get negative 100 over 7, which is approximately equal to 14.29 degrees per minute. Negative, because it's going down. But that doesn't mean that that is actually going to be the same for the entire time. You'd imagine if I drew a line further down, it'd actually have a slightly less steep. Why? Because as it gets cooler and cooler, it's going to slowly take longer and longer to get down. Different, if you have a look earlier on at a point up here, it's going to have a much steeper line, because as it just gets out of the oven, it's still hot, so it's going to quickly try to get to room temperature. Whereas when it's only a little bit above room temperature, it's going to slow right down to get to room temperature. Alrighty, so that is instantaneous rate of change on graphs.